Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel. Dear students, in this video we are going to study about various theories of light, such as corpuscular theory, wave theory, electromagnetic wave theory, and quantum theory.
Dear students, in this chapter Wave Optics, we are going to study about various topics such as theories of light, laws of reflection and refraction, phenomena like interference, diffraction and polarization, terms like magnification and resolving power of various optical instruments, and these optical instruments are microscopes, telescopes, etc. Now, according to James Albert Meissner, an age is called a dark age not because light fails to shine, but because of the people who refuse to see the light. Now, the theories of light. Before studying about various theories to explain the nature of light, let us see what is light. Light is a form of energy that is transferred from one place to another. A glance at the evolution of various theories of light put forth by scientists will give not only an overview of the nature of light, but also its propagation and some phenomena demonstrated by it. In the first case, let us study about the corpuscular theory. These corpuscles are nothing but particles, and this theory was put forth by Sir Isaac Newton. That was in the year 1672, and he gave this corpuscular theory of light, and that was already suggested by Descartes in the year 1637, and this theory explains the laws of reflection and refraction. According to this theory, light is emitted as tiny, massless, and perfectly elastic particles. These particles are called corpuscles, and as these corpuscles are very small, the source of light will not suffer any appreciable loss of mass even if they emit light for a long time. So on account of high speed, these corpuscles are unaffected by the force of gravity, and their path is a straight line in a medium of uniform refractive index. And the energy of light is obtained by the kinetic energy of these corpuscles. And when these corpuscles impinge on the retina of the eye, we have the vision. So this is how vision is produced in the human eye. The different sizes of the corpuscles give different colors to light. So this is how different colors of light is explained. When these corpuscles approach a surface between two media, they are either repelled or attracted. That means either repulsion or attraction will take place when the corpuscles approach the surface. The reflection of light is due to the repulsion of the corpuscles by the medium, and refraction of light is due to the attraction of the corpuscles by the medium. And this theory could not explain the reason why the speed of light is lesser in denser medium than in a rarer medium, and also the phenomena like interference, diffraction, and polarization. So, to explain the various phenomena, this wave theory has been put forth by Christian Huygens in the year 1678, and he proposed the wave theory to explain the propagation of light through a medium. So according to Huygens, light is a disturbance from a source which travels with a medium. So light is a disturbance from a source, travels that as a longitudinal mechanical waves through ether medium. So Huygens considered that medium as ether medium, which was assumed to pervade all space. And these waves will travel as a mechanical wave, and we know that a mechanical wave requires a medium for its propagation. So this wave theory could explain the phenomena like reflection, refraction, interference, and diffraction of light successfully. So the later experiments proved that the existence of ether in space, it is wrong. This naturally ether is not pervading space. So this theory could not explain the propagation of light through vacuum. The phenomenon of polarization could not be explained by this theory, because that polarization is the property of transverse waves. Next comes electromagnetic wave theory, put forth by Maxwell in the year 1864, and this theory, according to this Maxwell's theory, light is an electromagnetic wave which is transverse in nature, and it carries electromagnetic energy. And Maxwell could show that no medium is necessary for the propagation of electromagnetic waves, and all the phenomena of light could be successfully explained by this electromagnetic wave theory. The interaction phenomenon of light with matter, like photoelectric effect and Compton effect, could not be explained by this electromagnetic wave theory. Therefore, quantum theory has been put forth by Albert Einstein in the year 1905, and Einstein endorsed the views of Max Planck, and he was also able to explain the photoelectric effect, which we are going to study in 8th unit. And this photoelectric effect is nothing but the interaction of light with matter as photons, and that is to eject the electrons. What is a photon? A photon is a discrete packet of energy, and each photon has an energy E, which is given by this expression E equal to h nu, where h is called Planck's constant, and that has a value of 6.625 into 10 power minus 34 joules second, and nu is the frequency of the electromagnetic wave. As light has both wave as well as particle nature, it is said to have a dual nature, and it is concluded that light propagates as a wave and interacts with matter as a particle. So light can behave like a wave as well as like a particle, and that is why it is said to have a dual nature.
All right, let's dive right into this explainer and explore a centuries-long scientific battle to understand, well, what light actually is. I mean, for hundreds of years, some of the absolute most brilliant minds in history debated a question that seems so incredibly simple, yet proved to be astonishingly complex. What exactly is this stuff illuminating our world? Are we talking about a stream of tiny little particles, or is it a wave rippling through space? Figuring this out literally revolutionized our entire understanding of the universe. To quote James Albert Michner, "An age is called dark not because the light fails to shine, but because people refuse to see." For a really long time, humanity was completely in the dark about the true nature of light. Not for a lack of light itself, obviously, but for a lack of understanding. The journey to finally see how light works is this incredible story of fierce debate, and of scientists willing to look way beyond the obvious. So, here is our roadmap for today. We're going to start with the evolution of light, then dive into Newton's corpuscular theory, shift gears to Huygens wave theory, explore Maxwell's electromagnetic waves, hit Einstein's quantum theory, and finally, resolve it all with the dual nature of light. Let's get started with part 1, the evolution of light, the scientific relay race. You can kind of think of this history as this grand, almost epic scientific relay race. from 1672 all the way to 1905. Basically, each generation of physicists pushes our understanding to its absolute limit, eventually finds a fatal flaw, and then passes the baton to the next. Things kick off in the late 1600s with Newton and Huygens offering these competing ideas, followed by a massive gap until Maxwell in the 1800s, and then Einstein right at the dawn of the 20th century. So let's break down exactly what went down at each of these crucial milestones. Part 2. Newton's corpuscular theory, team particle. Okay, so our debate actually begins in 1672 with Sir Isaac Newton, who, brought immense authority to what we'll call team particle. Newton argued that light was made up of these tiny things called corpuscles, basically massless, perfectly elastic particles that shoot out from a source in straight lines. And because they move so incredibly fast, he argued they were completely unaffected by gravity. He even suggested that different sizes of these corpuscles are what give us different colors of light. So in his view, when these tiny, high-speed projectiles hit your retina, boom, vision is produced.
Now, the really crucial point here is that while these corpuscles neatly explained reflection via repulsion, they had some major fatal flaws. Newton theorized that when corpuscles approach a surface, they're either repelled, causing reflection, or attracted, causing refraction, which, was a pretty neat package. But it just couldn't explain everything. For instance, it failed to explain why light actually travels slower in a denser medium, rather than faster like his theory implied. And even more importantly, it completely failed to account for complex behaviors like interference, diffraction, and polarization.
So we're left asking, if light is a tiny particle, how on earth do we explain phenomena like interference and diffraction? Newton's theory was a great starting point, but it totally hit a brick wall when it couldn't explain how light could bend or, weirdly enough, interfere with itself. I mean, think about it. If you shoot two streams of particles at each other, they should just bounce off one another in this huge chaotic mess, right? They definitely shouldn't create the elegant, predictable bands of light and dark that we actually see in interference experiments. The physics just didn't add up. Moving on to part 3, Huygens wave theory, team wave. So enter Christian Huygens in 1678, delivering a massive rebuttal to Newton. He essentially became the founding father of team wave by proposing that light propagates exactly like spreading circular ripples on a pond. Every single point on a wavefront behaves as a source of secondary wavelets. When a ripple passes through water, the water particles themselves just oscillate up and down. They don't actually travel outward. Huygens argued that light acts the exact same way. And this wave theory beautifully explained the interference and diffraction patterns that Newton's particles just couldn't touch. But while Huygens solved the interference problem, his mechanical wave idea created a whole new headache. It required a mythical, completely invisible medium called ether to travel through. Remember, mechanical waves, stuff like sound or water waves, they absolutely require a physical medium to propagate. You obviously can't have a water wave without water. So Huygens proposed that light was a longitudinal mechanical wave traveling through this invisible substance called ether that supposedly pervaded all of space. Which brings up a pretty massive question. How does light travel through a vacuum if the ether doesn't actually exist? Because once the existence of ether was definitively proven wrong, scientists were really left scratching their heads, wondering how light even reaches us from the sun. Space is a vacuum. There is no ether out there. If light is a mechanical wave, the space between the Earth and the sun should be a total dead zone. Plus, Huygens' theory also failed to explain polarization, which is a property exclusive to transverse waves, not the longitudinal ones he was proposing. So once again, science needed a new champion. That brings us to part 4, Maxwell's electromagnetic waves, the refinement. Fast forward a bit to 1864, and James Clerk Maxwell brilliantly untangles the wave problem by introducing a completely new type of wave. He actually proved that light is a transverse electromagnetic wave, because it consists of electric and magnetic fields oscillating together, perpendicular to each other and to the direction they're traveling. It essentially carries its own energy. It doesn't need any sort of mythical ether to travel through. It can cruise right through the vacuum of space. Maxwell's theory perfectly explained reflection, refraction, interference, diffraction, and finally, polarization. But you guessed it, there's another twist. While electromagnetic waves totally conquered the vacuum problem, they utterly fail to explain how light interacts with matter, specifically how it ejects electrons. By the late 19th century, physicists thought they had the whole shebang figured out, but then they started messing around with the photoelectric effect and the Compton effect. Basically, when you shine certain frequencies of light onto a piece of metal, it knocks electrons loose. The continuous smooth energy of Maxwell's waves simply couldn't account for the math and the mechanics of how these electrons were being ejected. So the new mystery became, if light is purely a continuous wave, why does it interact with matter as if it's made of solid chunks? This glaring flaw set the stage for the final, honestly shocking twist in our centuries-long detective story. If light was just a smooth, continuous wave, its energy should theoretically build up over time to eventually knock an electron loose. But actually, that is not what happens at all. The interaction is instantaneous and it depends entirely on the frequency of the light. It behaves exactly as if the matter is being bombarded by tiny, discrete objects.
Which leads perfectly into part 5, Einstein's quantum theory, the twist. In 1905, Albert Einstein basically grabs the pendulum and swings it right back to team particle. After over a century of team wave dominating the scientific consensus, he realized that light isn't just a continuous wave, it's actually quantized into discrete, indivisible little packets of energy called photons. And the math here is that the energy equals Planck's constant times the frequency. When a photon hits an electron, it's this perfectly one-to-one particle collision. And just like that, he perfectly solved the mystery of the photoelectric effect.
And finally, part 6, the dual nature of light, the resolution.
So, after all that, who actually won this centuries-old battle? Was it Newton and Einstein, or was it Huygens and Maxwell? Well, the astonishing answer is both. Maxwell was entirely right about how light travels, and Einstein was entirely right about how it hits matter. When it's moving through space, bending around corners, or creating those beautiful interference patterns, light propagates as a wave. But the absolute second it interacts with matter, like striking a piece of metal or hitting the retina in your own eye, it hits like a particle.
So what you should really take away from all this is that reality is way, way stranger than fiction. Light is essentially both a wave and a particle, completely depending on how it behaves at any given moment. This is the absolute cornerstone of modern quantum physics. We call it wave-particle duality. I mean, we spent over 200 years arguing over which neat little box to put light into, only to discover that the universe genuinely does not care about our boxes. Light isn't just a wave or just a particle, it's a completely unique quantum entity that exhibits the properties of both. So I'm going to leave you with a bit of a provocative thought to ponder. If the very thing that allows us to see literally everything else in the universe completely defies our standard logic of either or, it really makes you wonder, what other incredible, totally counterintuitive truths are just hiding in the universe around us, waiting to be discovered? Keep exploring, keep asking those big questions, and I'll see you in our next explainer.